So in this video, we're going to talk about analog inputs. We'll go over what they are inside the test cell physically, and we'll go over how you're going to configure them within CyFlex. For starters, analog is an adjective used to describe the input, and it is defined as relating to or using signals or information represented by a continuously variable physical quantity such as spatial position, voltage, current, etc. So I've underlined continuously variable physical quantity mostly to point out that to distinguish between analog and digital inputs. Within a typical data acquisition system, you're going to have analog inputs, analog outputs, digital inputs, digital outputs. So your analog are going to have, generally speaking, an infinite number of points between 0 and span. So if it's a 0 to 10 volt, then it can be anywhere at any floating point value between 0 and 10, whereas a discrete can only be on or off. So analog inputs are used to measure voltage, current, and frequency. Now, generally speaking, voltage, current, and frequency aren't actually what you're interested in knowing. In a testing environment, you're mostly going to be interested in wanting to measure temperature, pressure, flow, speed, torque, something of that sort. And so in a testing environment, most measurement devices that you're going to be able to purchase that are going to measure those things are going to do so by converting that measured quantity into an analog current, voltage, or resistance value. And so long as that relationship between the measured quantity and the converted signal is predictable using some sort of mathematical equation or table, then within CyFlex we can convert back to engineering units, which is ultimately what you're wanting to know, whether it's just for monitoring, logging, or control purposes. So here's kind of a quick data flow diagram of what we really have going on. You might have an engine, and in this example we're going to be using compressor inlet pressure. So you want to measure the compressor inlet pressure. So what you're going to end up doing is plumbing to the input of a pressure transducer. Then that pressure transducer is going to convert that pressure into a voltage signal. You're going to have a cable running from the pressure transducer over to an I/O module, and then that I/O module is going to convert that voltage into bits essentially, and that's going to be done inside the controller for that particular I/O. Then that controller is going to stream those bits to CyFlex, to a computer that's running CyFlex. Then CyFlex is going to take those bits and it's going to convert it back into engineering units that you want, and then it's going to give it a variable name that you want. And so then you're going to be able to see that your compressor inlet pressure has a certain value. And that's kind of the big picture of what we're doing here when we're talking about analog inputs within CyFlex. So here's an overview of the programs that you're going to have to launch in order to get your analog inputs to work within CyFlex. So for starters, you're going to have a driver. In this example, we're using Snap.io server. We have a few other drivers that we'll go over. Once you've launched your driver, you're going to have to allocate channels, what we in CyFlex call channels. This is essentially memory on the computer that gets reserved and indexed so that it can be referenced later, and this is where the raw values are going to be stored. Next, you're going to see start continuous is in here, and I kind of jokingly put it's got to be in there. The reason I put that is you're not going to have to configure anything or do anything special for start continuous, but it's got to be in there. It won't work if it's not in there, so we're just going to go over where it needs to be in the Go script and kind of move on. Next, we'll have our transfer program. So our channels get allocated with AI attribute. Our transfer program is essentially then going to transfer those raw values through a calibration table and write to the variable. And that's essentially what's, you can kind of, I kind of think of it as the program that carries it from its raw state to its engineering units. It transfers it. Your calibration tables are going to get read in with this command called build tables. Build tables doesn't need any arguments, you just run it, and so kind of similar to start continuous, we're just going to tell you where to put it in your Go script. And then finally, AI specs is what's going to look at your input spec file and configure your analog inputs for the variable names, tell it what table to use, what units to use, etc. So here we have a list of files that we're going to end up going over in this video. Essentially, you've got the Go script. That's where most of your programs are going to be launched. When you start CyFlex, you've got an AI attribute file. It's essentially, you're going to run this program, and it's going to look at this file to know what it should do. You've got your /cell/tables directory. It's going to have a whole lot of different tables. These are your calibration tables that will be read in with this build tables command, and then essentially used by the AI transfer program to convert those raw values to the engineering units that you specified in your input specs file, which is the last file that we're going to look at. So now we'll go over the Go script. As I mentioned before, the Go script is where you're going to launch pretty much all of your CyFlex programs. So for starters, you're going to have to specify what rate you want CyFlex to update your analog inputs, or what frequency. And so these three examples show you how you're going to specify that. This first one is if you're using Modbus analog inputs, the second one's for Opto22 Snap series analog inputs, and the last one's for Gantner. You're specifying in units of milliseconds. And so whatever you specify here, like in this example for Modbus, the microsecond interval is 20. So every 20 milliseconds, it's going to check for a new value. If the data is stale, it'll essentially show that it's updated, but it'll just update it to the same value. Driver specification. So you're going to have to specify what drivers you want to start based on what I/O you have. And so these are some examples of the drivers you're going to start, and then an example of how they would be started. And so basically you're going to give it the name of the driver, the priority the driver should run at, your host IP address, the IP address of the devices you're talking to, and then for Modbus, the port and the Indianness of each device. And that you can see with these semicolons and 8502 and then Big Indian, or port 502 and Big Indian. Now ECAT server is MAC address based, so you don't have to specify the IP address, of course. And then one thing to touch on is for the priorities. If you're not sure what priority to run at, you're going to want to look in your .def directory. So go into CyFlex, cell.def, and then we're going to be looking at the Go script template. And so to know what priority we want to run Snap IO server at, for example, we're just going to search for Snap IO server, and we're going to see here in the example it says to run it at priority 24. eBlock server, it gives us the priority of 24. Modbus server, it gives us the priority of 20. So if you're not an expert in what priority what needs to run at, then look in your Go script in the /cyflex/cell.def directory. Next, you're going to have to run AI attribute. So AI attribute is actually going to create the channels, and it's going to use an AI attribute file. And so, as I mentioned before, the driver is going to write the raw values to the memory that you specify here. Start continuous, it's got to be in there. So if we look in the Go script, we just look for start continuous. And here we see start continuous takes one argument, and it is your input spec file. Next, you've got the transfer program. So the transfer program, here's an example of how you would start it. If you look in your Go script, you can see this is going to be started the same way. Gives it a priority of 19. We know that it should be 19 because we looked at our example. Specifies the slow rate, and it's worth pointing out, even though the program runs it slow, your update rate is still specified by the MS interval, as I mentioned before. And most systems are going to be run as critical. This plus C means that we're running AI transfer as a critical program. A critical program, if it fails to function correctly, it will trip the watchdog. If you're working on a system where the analog inputs are not critical, or for whatever reason you don't want the watchdog to trip whenever your analog inputs stop working, just don't start this with the plus C option. So you would just delete this plus C, and then it would not trip the watchdog if it stopped working. But generally speaking, you're going to want to leave that as critical. Next, you run build tables, and again, we just kind of look in here for build tables, and we see you just have to put build tables. You want to put it where this template is saying, but you don't have to give it any arguments. And so what tables are going to be read is determined by how you fill out your input spec file, and we'll go into the input spec file later, but basically there's a variety of types of tables, and on the very last slide of this PowerPoint we're going to have links to the documentation if you want to learn more about the calibration table utility and how cal tables are used within CyFlex, then you can go to that link. Next, we've got variable configuration, and so the command that you're going to execute to read the file that you've configured for your variables is AI specs. And so again, it's executed right after build tables, takes one argument, and that's the default. That's this spec file. If you don't give it an argument, it's going to use the default spec file. So with this file, you can configure your CyFlex variable name, which calibration tables you want to use for that particular variable, the default units to be displayed and logged, and the default precision, which is how many digits to the right of the decimal place do you want to display by default. There's also going to be some legacy items that are in this file, such as history, tolerance, compensation, but we'll get into that whenever we do our deep dive into input specs. And so that's essentially it. You just have to make sure you're launching these programs in your Go script. So next, we've got the analog input attribute file. So we're going to break this file down into two sections. We're going to talk about the header, and then we're going to talk about the actual channel definition. So for starters, we can just look at the attribute files that are configured on this system. And so I'm essentially running two attribute files. One is for Modbus, and one is just a dummy attribute file. So we'll kind of focus on this one for the most part as an example. So in this top section, you've essentially got a key name, an error name, and a driver name. So your driver name, this is going to need to correlate to the name of the program that's used for this type of analog inputs that you're using. So for this system, it's Modbus over TCP. Yours might be AI_snapIO. If you're not sure what it is, then it's generally good to go back to that CyFlex cell.def. And so here there's going to be example attribute files. So we can do ls-l on AI attribute. So here we can see an example attribute file for Modbus, for Snap, and for Gantner. To take a quick look at one of them, you'll see in this header you've got a different driver name. And so this one's AI eBlocks, whereas in this one it's AI Modbus TCP. Your key name is essentially kind of like a registered name. Each time you launch a new instance of this, you have to give it a name, and so this is where you specify the name. This is essentially the error name. It's kind of another program that's going to generate errors, and so this is what those errors are going to come from when you're looking in your error log. This and this you could change if you needed to. They just have to be unique. So you can't have two instances of AI Modbus TCP with this name. One of them, if you were trying to run two, you'd need to call it AI TCP2 or HSDA or something of the sort. So that's the key name, error name, and driver name. Other important fields, your channel offset. So to touch quickly on channel offset, on my system, if we look at the AI attribute, you can see I'm calling the AI attribute command twice. This one I give it no arguments, which means it's going to use the default file name of /cell/AI attribute.1. The reason it's 1 is on my system, the contents of this file in this directory are 1. So that's essentially how that works. So this is going to look at that file, which I've got open here, and then this one's going to look at this file, which I've got open here. So the reason we have this required offset is when you're running multiple instances of AI attribute, your channel allocation is going to start at 0, but you can just put an offset. In this case, I use 200, and so this line right here for device 1 is actually creating channel 200. This channel column, you're always going to end up, the actual channel that's created is going to be what you enter into this column plus the offset that you enter up here. So that's the channel offset. The number of boards, it's going to be an integer value, and it's going to count how many brains you have or how many controllers you have. And so the number that you put for your number of boards should always be the same as how you call your driver in the Go script. So coming back to the Go script, I started Modbus server TCP with one IP address. And so because I started it with one IP address, then in here I have a number of boards of 1. Looking at the example, this is commented out, but if it wasn't commented out, I've got my host IP address for starters, and then I've got 1, 2, 3, 4 IP addresses listed after. So if I were creating an AI attribute file for eBlock server, then the number of boards would be 1, 2, 3, 4. The max number of channels, this is essentially an integer value that needs to be equal to or greater than the number of channels that you're using. The reason you would want to make it greater than is as a provision for adding I/O down the road. So in this one I've got a total number of channels of 184, and then since this started at 0, this is the 184th channel, and then in here I start at 200. This is a dummy I/O system, so it doesn't actually matter in this, but for your system, if this was Snap and this was Gantner, you may want to leave 16, as I did, or maybe even more channels as a buffer in case down the road you add more analog inputs to this particular system. Because if not, you're essentially going to end up having to renumber your input spec file down the road, and although that's certainly possible, it's kind of a pain. So that's kind of why a lot of people will leave a buffer. They'll indicate a maximum number of channels, and then whenever they run their second instance, they'll use a larger number here. Other header entries should not be modified. This is pretty straightforward, but there's things like this pacer clock, timeout, etc. If I haven't gone over it in this quick tutorial, don't change it. Use whatever is in the default, and the default file that you're going to use is what you get from the .def directory. Now we'll move on to channel definition. So this is the bottom section of the file. So I kind of refer to this as the header, and then this as the channel definition. So here you're actually allocating channels and then specifying information about that specific channel. So for each one, you're going to give it a channel number, which is going to be an integer that starts at 0. And then, as I mentioned before, the actual channel will just be the channel plus the offset. The board index, so that's this next column. You'll see I called it the board index or eGate index or slave index. We kind of use a different terminology depending on what hardware you're talking to. So for Snap, Gantner, and Modbus, this correlates to the order you specify the number of boards in the header. So I mentioned that you've got the number of boards as 1. Here I'm actually listing all the boards. And so because I used a board address of 0 right here, then my slave index is 0 for everything. But if I had a number of boards equal to 2, and I had 0 and then 1, as you can see in this commented out example, then at some point I would end up adding a line, and this would be channel 16, and this would be index 1. So that's your board index, eGate index, or slave index. One more point for EtherCAT, this is going to be your master number. So if you're running EtherCAT and you have multiple masters on multiple ports, then you're just going to count them, 0, 1, 2, 3. MUX channel or Modbus address. This one probably gets the most confused. Here we've got the Modbus address. It's pretty simple with Modbus because it's just the Modbus address. If you're familiar with Modbus, you'll know that the device is going to have an address. I believe it's from 0 to 255, and you just put what its address is in here. For Snap, this is going to be the slot on the board. So Snap racks come in different configurations. I think it's 8, 12, and 16 slot boards. So for a Snap attribute file, this column is going to be either an integer value from 0 to 15. So if we take a look at AI attribute.snap, then we get down to this MUX channel, and here you can see integer values corresponding to what slot these modules are on the rack. For Gantner, there's a formula for this column. So if we look at the Gantner example, the header in this .def file kind of explains that it has to do with which UART it's on, or which RS-485 interface, and then what the module address is. If you've ever configured Gantner IO and Test Commander, those terms will be familiar to you. And so you just essentially apply the formula that's shown in here, and you'll calculate what needs to go in that column. We already talked about Modbus. For EtherCAT, this is the slave number. You'll run the EtherCAT slaves command. It'll show you all your slave devices, and then that's the number you're going to put in there. Next, you've got the board channel, module channel, or register. Same column, but it's kind of got a different definition, similar to here, for what type of hardware you're talking to. So for Snap and Gantner, this is just going to be the channel number. So if you've got a 4-channel voltage input module, then this is going to be 0, 1, 2, 3. So looking back at this example, for Snap, you've got 0, 1, 0, 1 for all these 2-channel, and then here we've got a 4-channel, and so it's just 0, 1, 2, 3. You should see similar terminology used in Pack Manager when you're configuring the Snap Brain. It's going to say that there's channel 0, 1, 2, 3. For Modbus, this is the register. So every Modbus channel has its own register, and so you're just going to put that register in this column, and this is going to read from it. And then for EtherCAT, it's the slave channel as derived from cstruct. So if you're familiar with EtherCAT, you've probably ran the EtherCAT cstruct command. You're essentially going to have to dissect the output of that to figure out what slave channel to use. Moving on, we've got gain and offset. These are kind of typical terms you've probably heard, but the gain is going to be a multiplier to the raw value, and then the offset is going to be an offset that you can apply to the raw input. So if you want to offset so that instead of it being 0 to 10, it's 1 to 11, then you can put in a fixed offset of 1. And then lastly, you've got this type column. So this is kind of fundamentally different for these two different types. So for Snap or Gantner, there's a table in the header that's going to give you a type code. And so this is what you're going to use based on what type of analog input module you have. So if you've got an analog input module with Snap that's 0 to 20 milliamps, then you're going to use 2050. But if you want it to be 4 to, or if it's 4 to 20, you're going to use 2051. If it can be either of these, like if the I/O module can be either, then which you use is going to determine which it is. It's going to be the same with Gantner. You see here's a header. These are I/O modules you should be familiar with, and there's a type code associated with them. For EtherCAT and Modbus, this has to do with the type of value that's being streamed. Short, float, long, unsigned long, etc. And what you're allowed to use is going to be in the header. So if we come back here and look at this Modbus example, we see down here there are these different types that are available to you. So for Modbus, the types depend on whether you're trying to read in from an input register or from a holding register, and these are the types that are available to you. So for this channel, as an example, I've got a voltage input module coming from Groove IO. I used a type code of 10 because in this case I was reading a float value from a holding register. Next, we've got the input specs file. This is where we go over, this is where we actually kind of configure the variable itself. So if we look at the input spec file here, this will be a good start. So when you're configuring your actual variables, you're going to have to go through and specify these things. So for starters, type. On modern systems, this will always be AI. That's this column right here. If you scroll up, you can see that there are also frequency inputs and counter inputs. These aren't really used very often to my knowledge anymore. They do still function, but these have mostly been phased out. Most frequency inputs, for example, if you're using a frequency input from Opto22, it's going to be configured as an analog input. Channel number. So this is where you can see 3 exclamation points. I'm coming back to the offset. So this needs to align with the channel you created in AI attribute. This isn't complex, but it's often forgotten and it can be frustrating. So I mentioned before, this is my AI attribute file. On my system, I'm running 2. I'm running 2 AI attribute files, this one and this one. They each have different analog input drivers. And I allocated this one, with a channel offset of 200. So now that I get into my input spec file, I scroll down, I see this starts at channel 0. These are coming from this attribute file, because this had a channel offset of 0. I scroll down, and then all of a sudden I jump from here to channel 200. These are my Modbus channels. These are created by this attribute file because I have this 200 offset plus 0. So the channel number, this is going to have to be this second column, And again, just be sure you don't forget your offset. And generally when you're editing or creating this file from scratch, you're going to have it open side by side with your attribute file to make sure you don't make any mistakes. Next, you've got a filter. You can do some digital filtering on the analog input. 0 is no filtering, 0.9 is high filtering, 0.99 is higher filtering. This filter, it's a recursive filter, and so it's going to be applied every time the analog input updates, and that's going to be determined by the ms interval that you specified in the Go script, which we talked about earlier. If you're not sure how exactly this filter works, it's also specified in the header. Pretty much all of the stuff that I'm talking about is specified in this header, so even if you don't have the PowerPoint available, you can always just scroll up. If someone's deleted this header on your system, look in the /CyFlex /specs.def directory and you'll find this header. Calibration table. So to know how calibration tables work, again, we go to the header, and it's going to tell us that there's this directory called cell tables, and that the tables are going to have this name that ends in a .tbl. So let's see that in action. So if we go to cell tables, we've got all these files that end in .tbl. And so here on this channel 0, I said I want you to use the error meter 0p table. So we'll copy that, and then we'll see if there's such a table, and there is. If we take a quick look at it, we've got some header information, and then we scroll down and see that this is an interpolation table, a 3-point interpolation. And so these raw values will be interpolated based on these 3 sets of points, and these values to get it to inches of water. So once we've specified calibration table, we're going to give it a CyFlex label. That's kind of somewhat straightforward. It's the variable name. So whenever you're referencing it, whenever you're doing, I guess I selected something else. Whenever you're doing a gvar, this is the variable name, or the CyFlex label. Units, this is going to give you the units. If you want to know what units are available within CyFlex, there's a couple ways. One is to type units. It's going to open a more session, and then you can hit enter to scroll through it, and you can find your units that way. I'm not a big fan of more sessions, so I tend to just look at the file. So I do CyFlex units.dat, and then I full screen it, and then here is another way. So let's say I know that I want inches of something, so I can search this, and these are my options: inches of water at this temperature, inches of water at that temperature, inches of mercury, etc., etc. If I wanted PSI, I can see there's mega PSI, atmospheric gauge, etc. So these are how you figure out what units are available to you, and then you just put them in this column. You can do it lowercase, you can do it uppercase, doesn't matter. The digits column, this is just the number of digits to be displayed to the right of the decimal. So I think the one that I was looking at earlier, you can see this one has a lot of decimal places specified. Well, that's because I said to display 7. If I wanted it to only display 1, and maybe I would want that because I don't want the operator thinking that that pressure transducer is actually accurate to 7 decimal places, because it's probably not. I could change this to 1, and then I rerun AI specs, which is what reads the spec file that I just edited. Now I only have 1 decimal place. And so you'll probably notice there's more columns in here than we talk about in this PowerPoint. Some of these are legacy, or they're kind of maybe not worth talking about because you're always going to do the same thing. So rate's always going to be slow. On older systems, you could specify the rate per channel. On newer systems, you don't. You always put slow. Compensation, this doesn't do anything anymore. History and tolerance, those are calculated automatically anymore. Don't delete these. If you remove this entry entirely, then it won't work. So you have to leave these in here, but if you put 1 or 2, it will make no difference whatsoever. You just have to have an entry there. So, lastly, diagnostics. What do you do when it's not working? You've configured all your spec files from scratch, you run a go, nothing's working. Okay. So there's a few tools available. The order of this maybe isn't best because really this one here that's third, it's almost always where you should start. If something doesn't work, check if there are errors. So these are my errors. You type ERRS, you get a less session. There's also an error viewer if you want a graphical way to see it. Towards the bottom of this, these are the errors that were started when I first ran my go. And then these are errors that came up later. This GVAR one is, you watched me make that mistake. So generally speaking, with I/O, it gets configured in the beginning of the go. So most of your errors that are related to I/O you will probably find towards the bottom of your error log. This system is pretty clean. You can see there's only 5 errors. It's almost guaranteed that you're going to have more than 5 errors. So you might have to do some scrolling on here to get to the bottom. But if you're troubleshooting analog inputs, you're probably going to end up scrolling to the bottom. The other thing that's worth noting is this app name. So you're going to want to look for errors related to the programs that we've kind of talked about. So earlier on we talked about Snap.io server. So you're definitely, if you're talking to Snap.io and Snap.io isn't working, search for errors from Snap.io server. Other programs, Start Continuous, AI specs, build tables. Any of those, if they're giving you errors, you likely have problems. And so you'll also notice this is an error, this is an information. This is just a message telling you something. In this case, it's telling me it connected to this thing. Information messages don't mean you have a problem. Error messages usually mean you have a problem. So the error log is where you're going to start. The bottom of the error log is probably where you're going to start. Similar or related maybe to the error log is the last go file. So you're going to have this file called the last go file. It's going to look strikingly similar to your go script because this is your go script executing. But if we, I mentioned we're going to look for programs related to I/O when we're looking for errors related to I/O. So Start Continuous. Start Continuous in the go script looks like this. This isn't in my go script. This is a message that was print to the terminal whenever I ran this go. Now, if your system is having errors, you might have some error message from Start Continuous saying it couldn't process your spec file. Here you see these information messages that were also in the error log. So this is often a good place to look specifically for I/O problems because there are some errors that get output to this file that won't go to your error log. Then we've got the driver test and get raw. So get raw is going to look at the raw value that's being written to the channel that was created when you ran AI attribute. So we've got our variable that we can see with GVAR. One thing you'll see a lot of people do is just kind of do this over and over. You can also just do a watch on it, and then every 2 seconds, watch is going to execute this command that I type over and over. what I'm doing here is I'm checking a couple things. One, is AI transfer updating the variable? Because it should be. If it says that it was last updated by AI specs, then AI transfer is not updating it and it's not working. The other thing that I'm looking for is this changing? And so if this is changing and it's being updated by AI transfer, then at a bare minimum, you've kind of got your architecture correct. The drivers streaming something from the device, the attribute file created a space for it to write to, and AI transfer is taking that, running it through a calibration table and updating it. Now, what if you don't see this updating, but you do see that AI transfer is updating it? Well, that could be a couple things. It could be that the raw value is not being updated. Or it could be that it's just not changing enough for you to notice. So a pressure transducer with a 0 to 10 volt output, you're always going to have a little bit of electrical noise. And you, depending on your calibration table or how much noise you have versus the span, you might not see this change at all, especially if you're not showing many decimal places. So a couple things you could do in that scenario. One, I showed you earlier that you can just edit the number of decimal places to display. But another thing you can do temporarily just for this session, and so this would go away if you did a slay stuff and ran a go, but I can just do a change res on this variable. So now I run the change underscore res command, I give it a variable name, and then I say, show me 7 digits. And then it tells me the format changed to 15 before the decimal and 7 after the decimal. You might not understand that, that's okay. But now if I do this, now I see all these decimal places. So if you were looking for just to see that your analog input is updating, but the value is going to be really close to 0, you can potentially do a change res and then do this watch on a GVAR, and then you might actually see it change. But maybe a quicker way is, instead of doing a GVAR, do a get raw. So a get raw is going to get the raw value of that variable. And so in this case, it looks like these are just integer values. And this is my dummy driver, so these values don't actually correlate to anything. But on your system, you might see a floating point value, you might see an integer value. It just depends on the hardware that you're talking to. But ideally, what you shouldn't see is 0.0000000, unless maybe it's a frequency input and you don't have anything on it. Then it probably should be reading that. But if it's something like a voltage or a current input, there's almost universally going to be some electrical noise. So you should see some movement either with get raw or with a GVAR. So those are a couple commands, get raw, and driver test. So driver test is kind of similar to get raw. You're kind of accomplishing the same thing, but through kind of a different way. So drv underscore test is how you're going to launch it. And this whole thing is terminal based. And so it's just going to ask us questions and we're going to answer them. So we want to see our analog inputs. It's asking us which program do we want to see analog inputs from. So these are the key names I talked about earlier. So let's say I want to see the ones from my dummy driver. I want them to be continuous. In other words, I want it to keep streaming the values. I'm going to use the 1,000 or 1 second interval. And now pick the channel you're troubleshooting, and you might have to kind of go through and do some counting and thinking about how you allocated your channels to know which ones. But let's just say that I know that I'm having trouble with channel 57 and channel 71. And now I'm going to hit D and say I'm done choosing. I'm going to hit enter, and then I'm going to hit 1 to start the test. And then I'm just going to sit and I'm going to watch. And so now I see some values being streamed. On the left I see channel 51, and on the right I see channel 71. Again, this is my dummy driver, so the values that I'm looking at right now are garbage, but on your system you might see something that's more meaningful. If you see 0.000000, and you know that the voltage should be reading 1, and it's being streamed as a float, it's not working. So what do you essentially get from kind of troubleshooting, you know, these raw values versus a gvar of the actual variable? Well, the point of these different commands is so you can distinguish between whether or not the data is even coming in versus whether or not maybe you made a mistake in your calibration table, or maybe there's a typo in your input spec file, and so when you read AI specs, it didn't process properly. So it's essentially trying to narrow down the problem. Earlier we had that slide where it kind of said we've got all these different programs. You know, you've got Snap IO Server, AI Attribute, AI Transfer, Build Tables, AI Specs. You could have a problem with any one of those. And we mentioned there's the different files that are configured, the Go script, the attribute file, input specs, and a calibration table. You could have an error in any one of those files. What you're trying to do with these is to narrow down where the problem is so you know which file you need to fix. Another thing, of course, you're going to want to make sure, however you started Snap IO Server or eBlock Server or whatever device you're trying to talk to in the Go script, you're going to want to make sure you can ping it. I really probably should have started with that. You're always going to want to make sure you can ping it. So if I was talking to this, I would copy this, I would open up a terminal, ping. If you get this, then nothing's going to work. 4 packets transmitted, 0 received, 100% packet loss. If you can't ping it, there's no chance that it's going to work. So you're definitely going to want to start with that. You're going to want to make sure the programs are running. Well, this system's not running. SnapIO, I should have done Modbus. So here I see Modbus server TCP is running. You may have some situation where the program was launched, but then it crashed. Well, that's going to cause problems. And so now you need to investigate why is it crashing. So with all of these, you know, your diagnostics, the fundamentals of diagnostics are narrowing down a big problem into small problems and because small problems are easier to solve than big problems. Lastly, in here we've got TCP dump or Wireshark. I'm not going to go into how to use those, but in a nutshell, TCP dump is a terminal-based command that you can execute. If you want to learn about it, you can Google it or type man TCP dump. What I use TCP dump for, I give it a source. I believe that's an SRC argument. I'm going to give it a source and I'm going to give it a destination. And so if it's an analog input, then the source I'm going to give it is going to be the IP address of the controller that I'm wanting to stream analog inputs to me. The destination is going to be me. And so that's going to weed out all of the traffic. And then I'm just going to stream that traffic. And what I'm going to be looking for is, are the values changing? It's going to be coming through as hex. A lot of it isn't going to make sense, but it doesn't matter. What you're trying to see is, are the values changing? If the values aren't changing at all, well, then the device isn't streaming fresh values. And so maybe you need to go into that device using the manufacturer's control software and reconfigure it. At some point, it might be streaming and it might be changing, but you still can't figure out what the issue is. Well, then it could be that you just run Wireshark. You filter for the source and the destination IP to be the Ethernet port on the CyFlex machine and that controller, and then you save that file and you upload it to a Jira, and then one of us can look at it and try to determine why it's not actually being turned into variables. Lastly, these are the links that I promised. So here you've got the .def files, and then here you've got some links to CyFlex.com on things like calibration utilities and how all that's going to work. And so I'll link this somehow to this video so that if you're going through this and you have more questions about some of these specific programs, then you can go to these links and get more information.